Okay, it's a pleasure to introduce our next speaker, Professor Gonzalo Tornaría from Universidad de la República. He will talk about an explicit Waldspurger formula for Hilbert modular forms. Please.
Okay, thank you. Thank you very much for the invitation to speak here. So my goal is to present a joint work with Nicolás Sirolli, who I hope he's around, on an explicit version of Waldspurger formula. This is ongoing work. We have. I will mention a theorem we published in 2018, and we are now about to publish a follow-up. So let me start by discussing the problem and the goals. In this slide, I'll start talking about classical modular forms. So let G be a new form of weight 2 plus 2k, level n, and trivial character. And a very, very interesting theorem of Waldspurger connects the central values of the L functions, the twisted L functions. Here, D is a discriminant. So chi sub D is a quadratic character. And we consider the set of central values for all the twists of this form G. And the theorem of Waldspurger relates these values to Fourier coefficients of modular forms of weight, of half integral weight. Okay, so this is a very interesting, a very, very deep result. And it's kind of explicit but difficult to read. So let me state an easier case when the level is odd and square free. Conan and Saguier, actually Conan and Saguier in 81 did this for level 1, and Conan in 85 did this for odd and square free level. So what Conan proves is that there exists a form F of half integral weight and level 4n, which will be in the so-called Conan space, and that's how he gets this form, and such that the central values, the twisted central values, are given by this formula. Lambda, I'm using lambda to denote the Fourier coefficients of F. So this is a very explicit formula. With the restriction that this formula works for fundamental discriminants, we prescribe quadratic conditions. So there's a condition on the sign of D, which has to do with the weight, and there's a condition on the quadratic character of D. So whether D is a square mod P or not, has to match these numbers, which are the root numbers of G, so the Atkin-Lerner signs at P, okay? So I should say it's safe to think this talk with assuming K is 0. So this is weight 2 forms and weight 3 halves forms. Of course, the result is much more general with arbitrary weight, but there's no, the techniques are very similar. So there's nothing to be missed if you think K is 0. Okay, so this is the starting point, an explicit version of Waldspurger formula for the case of odd and square free levels, and for a particular subset of all fundamental discriminants. Okay. The formula of Waldspurger is similar, but the constant, the term, there are more terms involved, and it's more complicated to state. So I should say the star here and everywhere, every time there's a star is a different constant, and well, I cannot and it's an explicit constant in each case, and I'm just not typing it, so it's easier to read. But in all cases, it's very explicit. Okay. Now we want to generalize this to get formulas for all discriminants. So here's what we can do. So I will use this set Sn will be the set of all prime divisors of n, and also the prime at infinity. And we pick an arbitrary function gamma, taking values plus minus 1 in this set. So this function gamma will give us different types of discriminants. And so again, under the hypothesis of n is odd and square free, we have this more recent theorem of Baruch and Mao, which says that there is a form, again, there is a modular form of half integer weight, which here I'm calling f gamma. So it depends on gamma, and the level also depends on gamma, but is roughly speaking is n times something. And in this case, well, the formula is very similar to the formula of Kohn and Sagier. And the point is, this formula holds for all fundamental discriminants of type gamma. So in the previous formula, gamma was a very particular function given by the signs of the Atkin-Lehner involutions. And here we are allowing arbitrary gammas. So in principle, this theorem gives you 2 to the t plus 1 different forms, giving all the values of all discriminants, at least discriminants coprime to n for here. I mean, the rest is a bit more general, but anyway. So as I say, this includes all fundamental discriminants prime to n. Baruch and Mao actually give a formula for all these discriminants, but I'll stick to prime to n discriminants. Okay. I should point out that when the product of all the signs in gamma is not equal to the sign of functional equation of G, the root number of G, it turns out if these numbers are different, then the root number of G twisted by D is -1. So this cell function here will have a negative sign of functional equation. So the central values will all be 0 just by trivial reason, and the forms f gamma will be 0 as well. So this really only works, you could say, I mean, this gives you a modular form f gamma half the time. Okay, but all this, the half the time that the other half the time, all the f gammas are non-zero. So you really get a bunch of modular forms, and all these are in Shimura correspondence to G, of course. But I don't want to go into that. But this is the sort of theorem that we would like to generalize. Okay, so okay, so here's the goal of this work. Well, first, before generalizing the work, a particular interesting goal from point of view of computation, for instance, or from point of view of finding properties about these central values, is to actually give an explicit construction of f gamma with explicit constants. Okay. Okay. I mean, the constants in Kohn and Sagier and in Baruch Mao are explicit in terms of the Peterson norm of f gamma. So you actually make they actually make an explicit formula. Which is sort of invariant by scaling, so it doesn't really matter which f gamma you get. Of course, if you multiply f gamma by a constant, you get the same formula. But one goal is to give an explicit construction with explicit constants. As I say, more general levels n, so even levels or composite, I mean, non-square free levels would be, I mean, all levels would be optimal. In practice, perfect square levels have some issues. So we cannot do perfect square levels in generality, and also, and here's this was in the title of the talk, to generalize these to Hilbert modular forms. So I will explain how to do this in a way that works for Hilbert modular forms over arbitrary totally real number fields. Okay, there's no restriction on, we don't place any restriction on the class number or anything. So that this means you have to be very careful on how you work with this, but and what are the Fourier coefficients, etc. But this can be made to work. So what are the tools we use to to get our goals? The first tool, the important tool is the spaces of Quaternionic modular forms. So I can't mention everybody that worked on this, but this started with work of Brand and Eichler, and the second ingredient is a Gros-Haguier formula for central values. So Gros-Haguier formula is very famous and very important for the derivatives of central values, but actually the formula in the same paper, they actually work out a formula for the central values. So there's a choice of a sign. So you do all this ranking Hilbert convolution stuff, and at some point you have to choose a sign. And if the sign is -1, you do one thing, and you get the formula for the height of the inner points, and related to derivatives of the L function at the central value. And if you choose the sign is +1, then you actually get a formula for central values in terms of the so-called heights of special points. Well, this formula has been generalized by Zhang, and the particular form of the formula we use is due to Xue. Okay, and the last ingredient is generalized theta series, which is how we are able to actually construct modular forms of half-integer weight with the coefficients satisfying this formula. So the way this works is we construct this generalized theta series in such a way that we can relate these Fourier coefficients to the heights of the special points in Chang's formula, and then we tie all ends and we get our formula in the way we want. Okay. So let me start with the Quaternionic modular forms. So quickly notation, F will be a totally real number field. Again, it's safe to think F is Q if you want, and forms are classical modular forms. I try to write things as if they were over Q, so it's easy to read. And there's still new results over Q in our work. So B will be a totally definite quaternion algebra of F. So that's a key point. We work with definite quaternion algebras. So our quaternionic modular forms are really algebraic modular forms in the sense that at infinity, the groups involved are compact and life is simpler. In a sense, we avoid analysis at infinity. So R will be an order in the quaternion algebra of discriminant n. In principle, any order will do. Later, we'll use a particular set of orders that gives us our results. We'll pick a unitary right representation of the quaternion algebra modulo the center. this will be the weight. Again, this is important in order to get higher weights. But if you're thinking of k equals 0, then v could be just it's just the standard, the trivial representation. So there's no representation at all. It's just complex numbers with no action. So it's safe to think that way for the talk. We use hat to denote ideals. If X is an ideal, then we think of the ideal as a left R ideal just by multiplying by R on the left, and we call R sub X it's the order conjugate to, locally conjugate to R by X. This is really the right order of the ideal Rx. So X is this, X represents an ideal when I think, when I think of X as an ideal, left R ideal, it also has a right order, which doesn't have to be the same. And that's what we're calling Rx. So that's for notation. And what are these quaternionic modular forms? So the way we deal with this space is, as I say, because this group, the group here is, the group here is really B cross mod F cross, okay? So because this group is compact at infinity, we can actually get away with ignoring the part at infinity. So we define quaternionic modular forms as spaces of functions defined on the finite ideals. This is much more convenient from a combinatorial point of view, from a computational point of view, and from also to do the proofs and stuff. And what we require for a function to be a quaternionic modular form is to be invariant in this way. So it's invariant by units, so this is the compact, and this is the discrete. So the action of the global quaternions is related to the action on V. So you could think it's an invariant. Anyway, so that's a small observation. So as an example, if you pick just one ideal and one vector V, then you can create a quaternionic modular form just by claiming that this form in the quaternion UX gamma is defined as V times gamma. So act by gamma. This is the action of gamma on V. So basically I'm saying pick a function such that phi of X is V, and then extend by the rules, and then take the everywhere else this is 0. So this is really supported on an ideal class if you want to think of this. So if you're thinking of weight 0, this really is, so there's no action. If there's no action, this is really constant function on ideal classes. So that's also a very, very classical way of thinking of quaternionic modular forms. In the easiest case, it's just functions on the set of ideal classes in the quaternion algebra. So one can define, won't enter into details. One can define Hecke operators. Basically, you take all the ideals of norm M and then act inside the quaternion modular form by that, and that gives a very, very nice operator. And we also have another types of operator, which are bilateral ideal operators. So these are sort of the analog to the Atkin linear operators. We take this group, which is all ideals such that the right order of Z is the same as the left order, say. So when you think of Z as an R ideal, it's bilateral in the sense it has the same order on both sides. So we take this group, this group is large, but modulo units and modulo scalars, remember F is the center, this is a reasonable finite group, and it acts in this way. So similar to the Hecke operators, but you don't have a sum. So this is very similar to Atkin-Lerner operators. And well, you notice in particular there's an action of the class group of F on I mean, the class group of F is included here, and usually for the Hilbert modular forms we work, one has to ask that they have a trivial central character, so that's the same as the class group acts trivially. So what I'm saying is, because the class group of F sits inside this group, this class group also acts on the space of modular forms, of Quaternionic modular forms, and we require this action to be trivial. So that's we're really working with trivial central character. Okay, so if you're thinking about Q, then the class group of Q is trivial, so there's no issues with the class group. But if we do this, I mean, if we restrict to forms with trivial central character, there's no issue about the class group of F could be arbitrary. So okay, so how are Quaternionic modular forms related to Hilbert modular forms? This is very classical, of course. Start with Brand and Eichler, two for classical modular forms. So we fix if you fix a weight k, I mean a vector k, there is a canonical way to choose a representation corresponding to weight to this weight k, which is you take the space of harmonic polynomials on this group. So this is sorry, this is a vector space of dimension 4, but this is a vector space of dimension 3 because I'm pushing out by the center. And so these are polynomials of 3 variables on each Archimedean place. We require this. We work with polynomials that are homogeneous of degree k, meaning k is a vector, so it's a weight. The weight could be the degree of the polynomial could be different in each variable, in each Archimedean place. And of course, well, this is our presentation, and in the sense the group we want acts by conjugation. Okay, so this is the representation you need to use to get weights. Again, if you want k equals 0, then just take complex numbers and no action, trivial action. So, but for the sake of completeness, the space of modular forms for of weight k, Quaternionic modular forms for the level R and weight k, we define as this. So that's what we get. And classic results put this in correspondence with Hilbert modular forms of weight 2 plus 2k and level n. So here you want to mention Eichler correspondence, Jekyll-Langlands correspondence, Peiser, etc. Many people that completed this. This is not a perfect matching. So one should be careful with this. There's some issues in the sense that, as in Jekyll-Langlands, for primes where the automorphic representation is a principal series, the quaternion has to be split. But given this restriction, you can in certain generality find Hilbert modular forms attached. I mean, you can always go from Quaternionic modular forms to Hilbert modular forms, but sometimes there's no coming back. And that's related to our issue with when the level is a perfect square. And the problem is that when the level is a perfect square, then it could happen that a Hilbert modular form is a principal series at all primes, and then maybe there's no Quaternion algebra that is split at all finite primes, unless F has even degree. So anyway, but the point to take home from this slide is Quaternionic modular forms correspond to Hilbert modular forms in some way. So, and anyway, so now here I'm talking about Hilbert modular forms of even weight 2 plus 2k. And now I will talk about Hilbert modular forms of half-integer weight. So how one can construct Hilbert modular forms of half-integer weight from our Quaternionic modular forms. That's the main interest in using Quaternionic modular forms. So you go from Hilbert modular forms to Quaternionic modular forms by Jacques-Langlands, and then you can get half-integer weight modular forms. So if given an ideal X and P, one of these spherical polynomials, I will define a theta series in this way. So basically, well, this you can think this as q to the delta of y. Delta is just a quadratic form, is the discriminant quadratic form on this quotient. So for a quaternion, you can take the discriminant of the minimal polynomial, and this is invariant by translations by scalars. So that's what you get. So you can think of this as q to the discriminant, and this is the spherical polynomial evaluated at y. So this is just a sort of classical theta series, generalized in the sense that there's this spherical polynomial, but this is really very classical, and this is proved to be a Hilbert modular form by Shimura. Okay, and okay, so this is what I mentioned. This is a Hilbert modular form of weight 3/2 plus k and some level 4n. The map, okay, here in order the level is a bit tricky. In order for the level to be really 4n, you need to put some hypothesis on the Quaternion order, but I won't give that. Moreover, this map, I mean, this theta is defined in terms of x comma p, but we also give an example of a Quaternionic modular form given by x comma p. So this is the minimal Quaternionic modular form that sends x to p. And I didn't mention then, but these forms span the Quaternionic modular forms. And so it makes sense, in a sense, they are a basis. I mean, if you take a basis of spherical polynomials, you get a basis of Quaternionic modular forms, and it makes sense to define a linear map in this way. And if you do that, it turns out this map is Hecke linear. Okay, this was proved by Sirolli in his thesis in a lot of generality. This was known before, in particular for over Q. And he proved over Hilbert for Hilbert modular forms, and the computation is very similar to the classic computation. But and also this theta series has this property that they produce they are invariant by the action of the bilinear the group of the bilateral ideals. Okay, which seems nice, but this is actually an issue in the sense that the modular forms of half-integer weight that one can expect to construct here have to be invariant in some way by the Atkin linear operators, and so this is really what causes what gives us some hypothesis on the Atkin-Lerner operators that we later have to remove by changing this. Okay. So now how we get to the Fourier coefficients. So I mentioned the Fourier coefficients were related to special points, and the way we do this is the set of special points. You can think the special points as quaternions, as ideals in the quaternions, with some equivalence class of them, and then what one can do is the set of special points for a fixed discriminant is a finite set, and you essentially sum these basic quaternionic modular forms where x moves over all this set of special points. So you're taking all special points of discriminant D, take the sum, and make a special quaternionic modular form in this way. Okay. TK is just a finite number. It's something to do with units. And the first proposition is that the Fourier coefficients of this theta series are actually given by this formula. So the Fourier coefficient at minus D, here D is a totally negative fundamental discriminant. So we take Fourier coefficients are indexed by positive numbers. So you take minus D, and I mean, we could take absolute value of D, but I mean, over F is a bit more tricky. What's the absolute value? So you take minus D here, and this is the formula. So the Fourier coefficients are just projecting onto this eta D. So you could think, you could also think of special points are, if you know about Higner points, special points are sort of analog to Higner points, and this is sort of analog to a Higner device or something. So anyway, so we have this formula here, which is not very hard to prove. And now we move to, sorry, I'll move to how we get to the central values. And I mentioned this formula of Zhang and Xue, this Gross-Aguirre type formula. And in this formula, we have something more particular. So here we have to, up to now, we haven't put hypothesis on R or D or anything. Here we'll put, this is the main hypothesis. So D is the discriminant of K. K is a quadratic field, and discriminant D, and we require that R contains the maximal order of K. Okay, and that's a strong hypothesis in a sense. And we construct this other modular form, which I call Psi sub D, is similar to eta here. It's similar to eta. It's a sum. But here, in fact, we are summing over the class group of K. So the fact that K, we fix an embedding of K into B, that gives us an embedding of the class group of K as ideals in the Quaternionic algebra, and so we can define this. And so in a sense, we are all of this. Because K has discriminant D, all of these will be special points of discriminant D, and it's like we are taking an orbit under the action of the class group of K in the set of special points. But so we are summing that, but we are not summing all special points of discriminant D, it's just a subset. And so suppose G is a Hilbert new form, etc. There's a technical hypothesis that the level cannot be trivial. because of well, issues on the computations, on the analysis. And then Shang gets this formula, which in this version state is due to Xue. Well, this version is our, I mean, it's a restatement of Xue's theorem in our language. And so assuming D is coprime, is odd and coprime to n, then this product, so it's the central value of G times the twisted central value, will be given by this formula. So here you start to see, well, the height product, the inner product for the Quaternionic modular forms. I didn't mention this explicitly, but there's a product, kind of like the Peterson product, and there's a formula that's it starts looking like the formula we want. Okay, so the only thing is, so you see, has the right shape. There is this constant here. So if this constant is, if this number is 0, then this gives nothing. So that's a problem that we can fix, but for now it's there. And this here, it's almost related to Fourier coefficients of the half integral weight modular forms, except not quite. I mean, this psi sub d looks like this eta. It's not exactly the same, but it looks similar. And eta gives us a connection to the Fourier coefficients of this theta series. So we have to still connect these two things. So basically the work that remains is to compare psi sub d with eta sub d. So that's what we need. Oh, sorry, I forgot to mention. So this G here means you actually are projecting this Quaternionic, this general Quaternionic modular form onto the direction of the modular form G. So this is the part of psi sub d where the Hecke operators have the same eigenvalues as the new form G. Okay. Anyway, so of course, when you do this projection, this might be 0, which then gives 0. This corresponds to this being 0. So it might be 0 for some reason on G, not on D. Anyway, so how we finish this? So again, we're assuming D is prime to n, well, the way to finish this is to realize that there's a connection, and it has to do with this group of bilateral ideals or Eichen-Leonard operators. It turns out if you take a form that is fixed by the bilateral ideals, by all the group of bilateral ideals, then really this formula, this projection to eta d is the same as projecting to psi sub d. Okay, so and remember, this was the Fourier coefficient of the theta series. So we are good here. I mean, in a sense, this is necessary because if psi is an eigenform not fixed by the bilateral ideals, then theta series is 0 because of this invariance by bilateral ideals that the theta series has. So this would be 0. So it can't possibly be. But anyway, and here's the proof of this proposition. So as we not just the class group of K. We use the fact that the class group K sits inside XD. This requires a fixing and embedding of K into B. But in general, what you can do is see that the class group of K acts freely on the set of special points of discriminant D. And this action the action of the group of bilateral ideals is free and transitive. So, well, you have to mod this also. This is the set of orbits. So you have orbits of this action, and the point is that the bilateral ideals permute these orbits. Okay, and well, the number of bilateral ideals is a power of 2. This power of 2. This is just the number of divisors of n. Here, I should say here we are using this hypothesis in this statement here is key. It's a stronger hypothesis about the order R. Okay, and so, well, then you put all together. I mean, now eta sub d is just, I mean, recall eta sub d was adding all over all the points of discriminant d, and this was adding only one orbit, you know, the first one particular orbit. And so if Bill R permutes, if this acts freely on these orbits, when we do this, we get all the orbits. So we get all the orbits, and this sum is really the sum over all special points of discriminant d. So that's roughly speaking the idea, and then it's just a linear algebra computation. Here we are using that this action is unitary, etc. So that's the end of the proof, right? So we move here, and because here is we are using that phi is fixed by the bilateral ideals, and here you can also see if phi happens to be an eigenform which is not fixed by bilateral ideals, then this sum here will be 0. So this is like this will be 0, as I say. So this doesn't really work in this shape. Okay. So now let me try to state the theorem, at least in the particular case, and then I'll make some comments on how we generalize this. As before, we have functions gamma. This is what we want. We want to fix a function gamma on Sn. So Sn, remember, were all the prime divisors of n together with all the Archimedean places. So we want to choose a sign for each of these places, and our goal would be to construct a modular form of half-integer weight for each of these gammas. Here in this particular case, I'll put this hypothesis on gamma. I'll ask well, roughly speaking, this is related to the hypothesis of Conan Saguier. If n is square free, then the valuation of n at p is 1, and then this is just saying gamma of p has to match the signs, the Atkin-Lehner signs. But let's do this more general version, and again assume d is prime to n, and assume k can be, the maximum order of k can be embedded into R. This is really a hypothesis about R. Okay, so let's choose this the Quaternionic modular form corresponding to G. So one has to check that this exists, but in this case will exist unless n is a perfect square, as I said. And so if D is of type gamma, then this form is really fixed by the bilateral ideals. So this is what the condition up here is, precisely the condition that gives us this. Okay. And so here's the proof. This assumption really means that this order R, I mean, in fact, the assumption of this order is sits inside R, gives a condition on the Eichler invariance of R. So it will tells us whether the Eichler invariants of R are +1 or -1 at the primes in N. But in particular, it tells us whether the quaternion actually is ramified or not at each prime. So this, again, this is really the hypothesis K inside B gives this set of ramifications. So B is not arbitrary; it's ramified at all the Archimedean places, and also at all places where g sub d of P to the power of BP of N is -1. Okay, so this would be by our hypothesis is this. Okay, so now how do we finish this? So this this is also classical. The set of bilateral, the group of bilateral ideas is generated by particular bilateral ideas, one for each prime dividing N. So this is the sort of the actual analog to the classical Atkin linear operator. There's one for each prime dividing the level, and they span the normalizer. And it turns out that the way ZP acts on a Quaternionic modular form mimics the way the Atkin linear operators act on the Hilbert modular form, but it's not quite the same. The sign changes when the Quaternion actually is ramified. So what I wrote here is this Quaternionic Atkin linear operator acts with the same sign as the classic Atkin linear when BP is split, and the opposite sign when BP is ramified. And so you can check. Recall, we want phi to be fixed by all bilateral ideas. So we want phi to be fixed by all CP. And so we want the Atkin linear operators act as the ramification of B. So this is what this condition here tells us. Okay. But with this condition, then we can prove for these discriminants of type T under this assumption. For now, this assumption, we have this theorem that we proved with Sirolli. This is in transactions of the AMS 2018. There is a modular form, a Hilbert modular form, F gamma of weight 3/2 plus K and level 4N, such that this formula holds. Okay. And for all D, okay, this should read for all D of type gamma. This is what you say here. Okay, this is for all D of type gamma. So for each gamma, there's one, and well, if N is square free, there's only one possible gamma. But if N is not square free, there's several gammas, and you have several forms. And of course, you can sum all the forms in some way or another and get one formula. But it's more interesting in this way. And the proof is just take this theta series associated to psi of G. Okay. And putting all that we seen together, you get this formula. So now let me make some remarks about this formula and the relation to Baruch-Mao formula at the beginning. So there is, well, first issue here is that this is restricted to certain types gamma, not all. That's the main problem with this formula as is here. Another problem, maybe more subtle if you want, is there's this factor here, which means, well, if this is 0, then this formula is just saying 0 equals, well, it has to be 0 equals 0, right? Otherwise it wouldn't be true. And this is an explicit rational, I mean, the star is an explicit non-zero rational constant. So it has to mean that all the Fourier coefficients of f gamma are 0. So when this is 0, f gamma is 0. For instance, if G has a negative sign functional equation, then this is of no use. But it could happen that this vanishes without even with plus sign functional equation. And so we have work where we have a work from this year where we expand this formula. I was going to write, but for the sake of time, I won't. Except we had a twist by an auxiliary discriminant L, and we get a similar formula. We get a different type of. No, I can't write in this program. Sorry. We get a different kind of theta series based on this auxiliary prime L, and we get a formula where the special value here is the special value twisted by L. So we can choose an L where this doesn't vanish. And more recently, we are finishing a work that hopefully will be published next year, where we actually show how to generalize theta series in such a way that we can actually construct the Hilbert modular forms f gamma for all gamma, no restriction on no such restriction. So we can really remove this assumption and get a similar result to this, except with the twisted by chi d here. And that is what generalizes the original Baruch and Mao result, obtaining enough modular forms of half integral weight to have formulas for central values of all twists by discriminants co-prime to n. And also in all these, there's really no restriction to n, except the restriction that comes from the fact that we want to have a quaternion algebra, and we want a quadratic field to be embedded in the quaternion algebra. And if you work this out, it comes out to the fact that you want n cannot be a perfect square. So this works as long as n is not a perfect square, and it even works for n a perfect square when the degree of f is even. So I'll stop here. Thank you very much.
Okay, thank you, Gonzalo. Are there questions for Gonzalo?
Sorry. I think my speaker.
I want to ask you a question. So
yes.
Looking at this formula, so it looks like you are in the good situation. In general, the issue is if you want to work with Shimura curves, for example, if you want to construct Higgins points, then what happens is that you need a field of degree odd to be able to have enough classes at infinity. So here's a concrete question that I think this should work. Suppose that you start with a modular form of level p squared over q, such that its principal series at p, okay?
Yes.
And what happens is that you cannot construct any Quaternion algebra in this case because it won't appear. I mean, right, you need the infinity place and p, then it's not there. But now if you choose a real quadratic field, any one you prefer, now you can change your form to this real quadratic field. And now the form will appear there because you choose your Quaternion algebra to ramify at the two infinity places and to be split at the finite ones. And then the form will appear there. And now what happens is that since you want to twist by a character of q, when you compute the twisted value upstairs, then the central value will split as the product of two central values of your original modular form twisted by your character and the twist by the real quadratic field twisted by your character. Okay. And then your formula is giving you a half integral weight modular forms such that when you restrict to characters that come from Q, it will split and will give you a product of the thing you are searching for times another piece. So do you think you can use something like this to try to construct a half integral weight modular forms in this situation?
I would say I had to think about it, but from just a quick thinking, I'd say it could be the case that the hypothesis implied that the signs of these two factors are opposite. So you're really producing a formula for the product of 2L functions with opposite sign of functional equation. And so this has to vanish. I mean, there cannot be a construction that gives a 0 here, right? The problem, I mean, I don't know. I will think about it. I haven't thought about this doing base change. May be interesting. Maybe it's a way to work around this. But the thing it happens when you have, I mean, at least over Q, when you have these kind of formulas, and imagine here you have a twisted by L and twisted by D, and all these formulas. If you want this to be over a definite quaternion algebra, you need L times D to be negative, and so anyway. But the local conditions, the local condition of this being a principal series somehow implies that the local root numbers will be opposite or something like that, and then the global root numbers will always be opposite. So
I think
this is what happened in this case. If you take your form of level p squared, which is a principal series at p, then I believe all the twists by positive discriminants will have one sign, and all the twists by negative discriminant will have the opposite sign. So something like this cannot possibly work. So I don't know if doing the base change fixes this or not, but I should think about it.
So you think that you have 4 terms and one of them will always vanish?
I think so. I think so. Yeah. I mean, there are 2 of these 4 terms will have opposite sign. That's what I think.
Okay. More questions or comments? Okay, if there are no more questions, we thank to the speaker again.
Thank you.